So in the last two modules, we had a look at the phenomenon of scattering from a crystal. Um, we got to know a very important principle from there, that scattering only occurs if the difference of the scattered wave vector and the incident wave vector is equal to the reciprocal lattice vector of the crystal on which a certain probe is incident. That is the Lovey principle, which is a very fundamental um, principle in condensed matter physics, which is another way of stating that crystals can only carry a certain uh, definite momenta in them, and those momenta are basically given by the reciprocal lattice vectors. But there's another utility of scattering experiments, and that they are used to determine the crystal structure of an unknown material. And in this shorter module, we would have a look at how X-ray diffraction experiments and the data from X-ray diffraction experiment can be used to determine an unknown crystal structure just by looking at the data. X-ray scattering experiments or X-ray diffraction experiments, they are done in various geometries. And before I go into interpreting the data from experiments, let's try to summarize a few commonly used geometries, experimental geometries of X-ray diffraction. So the first two which I would discuss here are based on single crystals. So these methods assume that the sample you are using is a single crystal overall. Um, One of the methods we have already discussed is the so-called rotating crystal method, in which what you have is a single crystal as your sample and an X-ray incident on it, and there is a photographic plate which captures the scattering from this um, uh, crystal. So normally you don't have any diffraction, but you have to rotate the crystal about different axes to obtain the diffracted spot on the photographic plate. So you get such a diffraction pattern, and from this pattern you can determine what crystal structure it has. This rotation is done to, as we showed earlier in one of the module, is that you have an incident wave and you have a scattered wave, and you can find the difference between these two waves, and you rotate the crystal until the difference between the two is equal to the reciprocal lattice vector. So the starting point of this difference vector and the ending point both are on a reciprocal lattice point, and this is the condition which is the Lovey condition. So the Lovey condition is satisfied by uh, rotating the crystal. So at a certain rotation angle you might satisfy this Lovey condition for a specific crystal, for a specific condition like this for a specific g vector, and for other angles you might specific angles you might satisfy it for other g vectors. So when you have exhausted all the angles, you would get a complete diffraction map. The other method which is used is so-called Lovey method. So it's again what happens in this case, you have incident X-ray on a crystal and you try to form a diffraction pattern, but it's not formed that easily. So what is done here is that the X-ray frequency or the X-ray wavelength is tuned continuously, and they're tuned. So what you are doing here is you are changing the wavelength of X-ray, and by changing the wavelength of X-ray, you are basically changing the magnitude of this k and k prime vector, and you keep on changing, uh, keep on doing this, and as you do this at certain specific wavelengths, the diffraction condition, which is this one, is satisfied, and a diffraction pattern is developed. So both these methods, they have their own way of satisfying this Lovey condition for scattering. In one case it is by rotating the crystal, in another it is by changing the magnitude of the k vectors itself. But the problem with a single crystal is that not most of the material are single crystals. So, and most of the material, a large class of the material, are polycrystalline material. So you can't use the previous method for a polycrystalline material. Uh, so there's another method which is Debye-Scherrer method, which is the most commonly used um, method for polycrystalline material, and in general is the most commonly used X-ray diffraction method for determining the crystal structure. So in this case, the sample is usually taken as a powder. So the powder consists of crystallites. So crystallites are small crystalline grains or small crystalline pieces. So you have a perfect crystalline order in this region, but in the next region, it's slightly oriented differently as compared to this one. So that's the sample, the corresponding sample is a polycrystalline sample. So in this case, you would find these small grains and like many such small grains of micron sizes in a sample, such that you find all the orientations um, possible in this orientation of the crystal possible in this sample. So in this case, what it done is the incident X-ray is incident on this polycrystalline sample, and it gets diffracted from it. So in this case, because you don't have one crystalline piece, but you have several different crystalline pieces, and what happens because of that is because they can occur in various different orientation. So the result is that you have not one diffraction peak, but rather a cone which emits from a particular um, set of family planes. So for a specific HKL, which is the reciprocal lattice vector, a full cone of scattering is um, uh, emitted or scattered around a certain azimuthal axis. This is entirely due to the fact that you have all these different geometries possible. So you can look into detail why such a cone is formed. But to let you know that just a specific HKL or a specific reciprocal lattice vector in this scattering corresponds to one cone of scattered light. So what do you get as a result is when this experiment is done, you on this photographic plate which is surrounding the sample, you get a recording of this diffraction pattern. So each uh, projection of the cone, which is a circle on the photographic plate, represent a specific set of lattice planes. And you have so what do you have is so 2 theta equals to 0 would corresponds to directly the beam which directly goes through, and 2 theta equals to 180 corresponds to the scattering such that it is reflected back. So that's why you see these two holes here. So these two, one hole represent 2 theta equals to 0, and the other represent 2 theta equals to 180, and you have all these different diffraction um, rings. Um, so in modern experiment, what you don't have photographic plate, but rather you have an array of detectors aligned in a circle, uh, charge coupled devices or CCD devices, which you all also have in your camera. So instead of you getting such a ribbon of photographic plate where this corresponds to 0 degree, and as you go you have the angle increases. So instead of these rings which you obtain, what you get in a CCD array is just an intensity at particular scattering angles, and these so this is also called a spectrum of X-ray diffraction data. So either you get rings like that and you analyze the rings, or you get such a lines like spectrum. So another method, another geometry, experimental geometry to detect scattering or diffraction from a powder sample, which contains many crystallites. is that of a rotating geometry method. So it creates data exactly like that of a Debye-Scherrer data, but the experimental setup is slightly different. So what do you have is your powder sample oriented in a certain direction and is placed on a certain platform. Then you have a source of X-ray which is installed at a certain location, and you have a detector of X-ray which detects X-ray, scattered X-ray at a certain specific location. So if uh, this T, which is the source of X-ray, let's say it makes an angle theta with the surface of the sample, then the reflection is again by a surface by an angle theta. So the total angle between the incident ray and the reflected ray is 2 theta. So normally all the data, that's why all the data is plotted with respect to 2 theta, because 2 theta is the angle between the incident k and the scattered k. So for this specific 2 theta, you can record the data, and what you do is then you rotate the detector as well as the sample without rotating without changing the position of the source. So when both of these are rotated, so basically you are detecting a different recording theta at a um, signal at a different 2 theta values. So this is rotated about an axis of rotation going through O, and this detector is rotated by the same angle. Basically theta is changing and 2 theta is changing, and you keep on doing this and record the intensity at different 2 thetas. So once you do this, you can plot this intensity as a function of 2 theta, and what you find out that at specific 2 theta values you get very like sharp peaks if you have crystallinity in the um, in the sample or in the unknown sample. And then there are ways to, so you get all these different peaks, and then you can label these peaks by their corresponding Miller indices, and once you do this you already know what crystal structure these crystallites have. And today we would look into this problem of how to label these peaks and from such a powder method, and also how to find out what crystals. So just to let you know what does these different peaks mean. So you have the small crystallite in the sample. This is the source of X-ray. This is the detector. So at a specific 2 theta, let's say you have the condition of constructive interference at the detector is satisfied for this set of peaks, which is peak, let's say, uh, 0, 2 peaks, which are these. So you can, these are highlighted, the crystallites which have which produces these diffraction from these particular set of peaks are highlighted here. So at this particular 2 theta, where this condition is satisfied for this particular peak, you would get a corresponding peak for that in your diffraction data. Your sample and your detector at a certain other angle, the diffraction condition might be satisfied for another set of data, which is shown set of planes here, and you would get a peak corresponding to that set of planes. So, and you keep on rotating the sample and the detector until this condition is satisfied, and you get a full set of peaks uh, in your X-ray intensity plot here. Just an example, I would start with the X-ray spectrum or X-ray diffraction of an aluminum sample. So let's say you have an aluminum crystal and you do such an X-ray experiment on aluminum, and you want to find out that what crystal structure aluminum has. So just to show you, this is the experimental data from an actual aluminum sample. It's again a powder sample, which means that the sample consisted of small aluminum crystals. One important information you need to know is what X-ray wavelength you use for this experiment. So that is normally you can find out from the from the setup from the X-ray source which is creating this incident X-ray. So uh, the more precise you know the value of this X-ray wavelength, the better it is. So this is something you start with. And apart from this, what do you get is a data like this from or a spectrum like this from your experiment. So what do you have here is 2 theta, which is the angle between the incident and the scattered um, X-rays, and this is the intensity of scattering. So you don't have any scattering at these angles, and then there's a sharp intensity in the scattering at a particular angle. Again, there is no peak, and then there's again a sharp peak, and so on. So each of these peaks represent a reflection or scattering from particular set of planes, and our task is to find out which planes these are in the case of aluminum. Just to recap, we found out for simple crystal system that you can have all these set of planes with you represented by their HKL, and in a cubic system all these different set of planes, they are valid set of planes, and they won't leave any lattice points out. But in the case of BCC and FCC, some of these are missing planes, and last time we in the last module we calculated it. Why is this the case? For example, in BCC, if the summation of H, K, and L index is an odd integer, then that is missing. For example, in the case of a 100 plane, but 110 plane, 1 and 1 give to 2, which is an even integer. So this plane is missing. So you have kind of a selection rule for a BCC. Similarly, you have a selection rule for an FCC, which tells you that all three HKL should be either even or it should be odd. For example, this is odd and these two are even, so this is absent in FCC. But in 111, all three are odd, it is present, and so on and so forth. So you have this information is important to this set of data is important to um, understand the crystal spectrum, and that's something which we would utilize. You the same data can be written in different form is like, let's say for example, these are all the Miller indices. In a simple cubic system, all these Miller indices are possible apart from a few which are missing, but all these Miller indices are possible. These missing elements are due to the symmetry of the crystal system. For example, because the seven so this is the set of lines which would corresponds to all these HKL combinations. Now, in a body-centered cubic system, some of these lines would be missing because of the selection rules. In the FCC lattice, some other lines would be missing because of the selection rule. But nevertheless, this is the pattern you get in a body-centered cubic, and this is the pattern you get in a face-centered cubic. And you can do a similar kind of calculations which we did in the last module for diamond as well, and for hexagonal, and you get data like lines like this, so corresponding to specific HKL combinations. As hexagonal is normally separate from a cubic system because the c-axis has a different length in the hexagonal system, so that's why they are mm, written separately. Okay, so we would use this data, this information here to coming back to the data. We have to interpret this data. Procedure to interpret this data. So first, what you do is you know the wavelength of the incident ray with good enough accuracy. So as we already knew that the better the accurate you know the X-ray incident X-ray wavelength, the more accurate would your calculations be or interpretation be. Then what you do is you take your spectrum and you calculate accurately the angles of all the peaks which you see in the X-ray diffraction data. And by angles, I mean 2 theta and not theta, because each peak is at a certain 2 theta value. Then you use the Bragg condition. So the Bragg condition is that of a constructive interference, because each of these peak corresponds to a certain constructive interference condition. Uh, so just to let you know that the diffraction order we see is the first order. So n here is represent the order of peaks. So the diffraction data we usually look at is the first order data. There are second order peaks which occurs at larger angles, but we don't consider them. So keeping n equals to 1, d is something which is the distance between the lattice planes from which the constructive interference is occurring, and theta is the angle which is made the angle between the surface of the sample and the incident X-ray, and lambda is the wavelength of the incident X-ray. And from this Bragg condition, you can extract d, which is the lattice, the inter interlayer distance between the atomic planes, simply given by L by 2 sine theta. Then to interpret the data, we normally assume that the crystal is a cubic system. Why we do so? Because it makes the calculation and interpretation a bit easier. And secondly, most of the material, they do possess cubic structure in either of these three forms. So it's a good guess to start with, that the unknown crystal structure which you want to find is a cubic system. If none of these the steps which is shown here, they give you reasonable result, then you can start looking for other crystal systems like non-cubic, like hexagonal cubic systems. But you start with the assumption that you have a cubic system. And the nice thing about cubic system is that the interplanar distance for a specific set of planes HKL is simply given by this a by h square plus k square plus l square root. And you can rearrange this formula into a square by d squared equals to h square plus k square plus l square equals to n, where n is simply the squared sum of these Miller indices for a specific set of planes. And this n would play an important role in identification of the peaks. So you have all those different peaks, and for each of those peaks you can find the d, and then what you do is you then assign the first d value of the first diffraction peak and make it equals to a. Then you square this a and divide it by d square of all the values, and you would get some numbers for all the peaks. If those numbers are integers, then that integer value is your n. If those are not integers, then you have to multiply it by some number to make it integers. And so this procedure would become clearer. So why this n is important? So as you can see, like once you get n for all the peaks, so let's say the n for the first peak is 1, n for the second peak is 2, and for the third peak is 3, then you already know that you have a cubic system. But if n for the first peak is 2, and the second peak is 4, and the third peak is 6, then you know that you have a BCC system, because n for the BCC has this combination, and for FCC the uh, n start from 3 rather than 1. So the value of n for the first peak immediately give you this information that whether you are dealing with a simple cubic system or a BCC system or a so the idea is and then you look for these systematic absences which ends are missing, and that would give you already a good estimation of what crystal structure you have. If you don't have if these steps doesn't give you a good idea, then you either look for a non-cubic system, like for example, whether it can be a zinc blende or a diamond or an hexagonal closed packing system. So that's so you have these peaks uh, plotted as a function of 2 theta, and you measure the position of those peaks as accurately as possible. So this peak number A, which I have labeled as A, it occurs at 2 theta equals to 38.43 angles degrees. B occurs at 44.67 degrees, C at this degrees, and so on and so forth. So I have labeled all the peaks and found the as the accurate angles as possible for the 2 theta values at which they occur. I arrange these peaks in terms of ascending order, A, B, C, D, in terms of ascending 2 theta degrees, shown here. This information I already have. Now I can use this Bragg condition to find the interatomic distance, D. So where D is simply given by lambda, which is here by 2 sine theta. So you get the theta from these values, may, take a sine of it, multiply it by 2, and then you calculate this value for all these different peaks. So you get this as your uh, these are your proposed interatomic distances or interlayer distances between the set of planes. Then what you do is you take your first D as your A, you square it. So you take this as your A, you square it, and then you divide it by D square, where D square are all the entries here. So of course the first one would give you 1 because this is your A, and A squared by the same value gives you 1. But this A squared, which is the square of this, divided by the square of this, doesn't give you 1, it gives you this value, and so on and so forth. So you get this A square by D square for all these values. And now you look for if those are integer values or not. These A square by D square, it should be ideally equals to N, capital N, where capital N are integers. But you look here and they don't look integers. So you have 1, then you have 1.3, then you have 2.6. So they are not close to any integer list of numbers. So what you do, you multiply it by some number. Let's say you multiply it by 3. So you multiply it by 3 and you have these set of numbers, and lo and behold, you have numbers which form a list very close to integer values. So 3.00, of course, 3, 3.999 is almost 4, 8 is on 8, 11, 12, 16. So you have a very nice list of integer values. So as we said earlier, that uh, n should be a list of integer values. Now we have to look for which crystal system it has, because here n starts from, if you look at your table here, n here start from for cubic system, the first value of n is 1. For the BCC system, the first value is 2. For the FCC system, the first value is 3. And that's why you can already say that your system, the unknown system which you wanted to find, is an FCC system. No, so we know these n's corresponds to FCC system, but we can also try to find some other properties of your crystal system. For example, what is the lattice constant of the unknown crystal system? Because there's an important property of, so we know that it would have an FCC crystal structure, but what are the uh, uh, lattice constant? So uh, for each value of n, we know the specific combination of h, k, and l as given from the previous table. So these are 111, 200, 220, 211. So basically the peaks which we had labeled before as A, B, C, D, we now know that which set of planes they do correspond. So since we know now the HKL indices of these each of these planes, and we know the inter layer distances for these planes, so using this formula, just I can rearrange it like this, and I know D for each of these HKLs, and I know the HKLs themselves. So what I can find is A, where A is the lattice constant, or which is the length of the side of the conventional unit cell of the face-centered cubic system for aluminum. And if I do this for all these different planes, turns out to be quite a consistent number with very good accuracy. And this accuracy is mainly coming from the two things: the accuracy of the measurement angle and the accuracy of the X-ray wavelength. uh, how accurate you know that. So you have a very good value, a very precise value for the latest constant of an aluminum crystal system. Now, I had labeled all these planes with the corresponding Miller indices, and I know the crystal structure is a face-centered cubic system, and I also know the lattice constant for the unknown crystal, which is that of aluminum. So I've just rearranged the data a bit, just to look at it again in a slightly different way. So I've rotated the spectrum like this, and I know this pattern for different crystal system. And you can, just by looking at the patterns, you can immediately identify which crystal system this spectrum belongs to. So if you look this at this one, this is more or less a body-centered cubic system, so more regularly arranged. Of course, it can't be a simple cubic system because this is too close. Uh, there are certainly certain peaks missing here. But if you look at the face-centered system, you have two close peaks here, which are here. Then you have a gap and one solitary peak, which is this one. Then you have a relatively smaller gap and two peaks again, relatively smaller peak gap and two peaks again. So just by looking at the pattern, you can also identify which crystal structure it is. So this table, this kind of table is quite handy, and some people just immediately look at, if you are have enough experience, just by looking at the spectrum, you would immediately identify what crystal system so it is. Just to summarize, we have for this, we have a lattice constant of this, which was previously unknown. We found it from the crystal structure. We identified all the peaks coming from a certain lattice planes, and we know that the crystal system is the FCC crystal system. To let you know that the lattice constant which you measure is that of a conventional unit cell, the length of the side of a conventional unit cell, and not the interatomic distance in the aluminum crystal itself, in the FCC crystal. So once you do this peak leveling, another important aspect of these peaks are not only the angle but also the intensities. The intensities also carries valuable information and can be used to identify specific crystal structure, because in some cases it might not be easier to identify the crystal. The intensity or the scattered intensity, it is proportional to three factors, and we would discuss them, each of them separately. So the scattering is directly proportional to the square of the structure factor, which we already have seen here, but it's also directly proportional to m, where and it's also directly proportional to this other factor. So let's look at this m factor here. So m is the multiplicity of a specific HKL. So this bracket HKL, in such kind of curly bracket, it represent equivalent planes which are identified by the same index, but there can be many members of this plane. So, and m is the multiplicity of this these this kind of a notation for 100 set of planes. So in 100 system, this 001 is basically the same as 100, is basically the same as 010, depending on from which side you are looking at the crystal. So an incident X-ray which looks at a crystal which has many small crystal pieces, it won't identify between this set of plane, this plane or this plane or this plane. All of these three looks the same, and the scattering from these three would exactly be in the same plane, in the same 2 theta, because the condition would be satisfied at exactly the same theta for all of them. So this set of planes would has a multiplicity of 6. Then you have a 110 plane, and a 110 plane. You have different members of this 110 plane. So 0, 0, 0, 1, 1 and 110, they look exactly the same if you look at the crystal from a specific angles. And you have the 110 set of planes has a multiplicity given by 12. Similarly, a 111 have a multiplicity by 8. So it's basically how many different combinations you can have of the same Miller indices, is basically the multiplicity number. The intensity, the higher the multiplicity number, the higher the intensity. So that's an important thing, because then if you have higher multiplicity, it means you have higher uh, different uh, different planes exactly representing the same Miller indices, and the higher that number is, the larger would be the scattering amplitude. The second important thing is factor in the determining the intensity of the scattering is the structure factor, which we have talked about in detail in the last module. But the structure factor is equals to a certain atomic form factor multiplied by a phase, which let you know which combination of HKL should be missing or not. But atomic form factor is something which for an X-ray, it depends on the reciprocal lattice vectors. We had looked at this problem, and we said that this structure factor for an X-ray is G dependence would mean that, or that of the atomic form factor G dependence would mean that the larger the 2 theta is, or the larger the scattering angle is, the smaller is this factor, and the smaller is the intensity of the scattered. This structure factor S squared, it tells you that the peaks at the larger angles should have smaller intensities. Then you have this geometrical factor, a so-called Lorentz geometric factor, which is entirely due to the geometry of the experimental setup, and it has nothing to do with the experiment, with the sample itself. So it doesn't depend on the crystal structure, it only depends on the circular geometry of the measuring setup. And this Lorentz geometric factor, it is given like this. It can be calculated for such a geometry. It turns out to be something like this. It is very large at a smaller angle. It's increasingly becomes smaller, and it rises up at 180 degrees. So if you remember this Debye-Scherrer experiment, you have higher intensity near the 0 degree, and you have and as you go away towards 90, the intensity becomes smaller and smaller. As you go to 180, the intensity again rises up. So that's exactly what you see here. The same is true for this geometry as well. So what does it tell you? That up to, like, let's say 120 degree, as you go away from the 0 degree, the intensity of the line should decrease because of this factor. So just to summarize, this intensity of scattering depends on these three factors. This one depends entirely on the multiplicity of HKL, so it doesn't have any angle dependence. It only have how much multiplicity does a specific HKL combination has. This is definitely for an X-ray diffraction is angle dependent. So this tells you that this factor that at higher theta up the intensity should drop. This factor again tells you that the intensity should drop as you go towards 120 degree, but it would rise sharply at 180 degree again. So let's use this information about X-ray diffraction, intensity of X-ray diffraction data to interpret X-ray data for iron. And this is the X-ray spectrum for iron. So this is 2 theta, and this is the scattering intensity. You are looking at 3 peaks. You can again do the same exercise of finding the angle, 2 theta angles for each peaks. You can make a table. You have A, B, C, D, 3 different peaks. angle to theta for each one of them. You can find the interplanar distance for each one of them. Then you can select this as your a, square it, and then square divided by d square, and this is what you get. D square by d square, if you look at this number, you just multiply it by 1, or if you don't, just leave it here. These are very close to integers, so they can be your n's, which would be 1, 2, 3. And this would correspond to a simple cubic system, because for simple cubic system n start from 1. But you can also multiply it by 2, and if you multiply this a square by d square by 2, you get these two numbers, which are again very close to some integer combination, which is 2, 4, 6. And 2, 4, 6 represent a body-centered cubic system. So which one, if this is true, if this is true, or that is true? And the answer is in the intensities of these three peaks. So especially these two peaks. So uh, let's look at the intensity. Intensity depends on the multiplicity, which is this number. Uh, Apart from these other two factors. So let's look at take it as a simple cubic system, which would be corresponds to n equals to 1, 2, 3, because in simple cubic system these 1, 2, 3 peaks are present for n values. So if I take this as a simple cubic system, this central peak, which is the second peak, should have a multiplicity of 12. This one has a multiplicity of 8, which means that this should be stronger in intensity than this one, because this one has a higher multiplicity. Indeed, it's not true. Let's look at this a second combination, which tells you that it's a BCC system, because you have a n equals to 2, n equals to 4, and n equals to 6 as well. And here, if you multiply it by 2, so let's check if this is true. So for this one, for this peak, which is capital N equals to 2, you have multiplicity of 12. But the important one is this one, which is 6, which has a multiplicity of 6, and this has a multiplicity of 24. So this is, it means that this peak, the middle peak, should be smaller in intensity as compared to the third peak, and indeed that is true. So what we can refer from here is that this FCC, this crystal is indeed a BCC crystal, and you can find the corresponding Miller indices for each of these peaks, and also the lattice constant thereon.